This is the most important question from this chapter. Hey, welcome back everyone. Now let's move on to our next chapter, that is chemical equilibrium. For first we are starting it with what is chemical reaction. It is a process in which two or more reactant react to form one or more product. Fundamentally, chemical reaction is of two types. First one is reversible reaction and second one is irreversible reaction. Now move on to our chapter, that is chemical equilibrium. In chemical equilibrium, concentration of the reactant and the concentration of product does not change with the time, and the system does not share any further change in the properties. Simply, if rate of forward reaction equals rate of backward reaction, it is said to be chemical equilibrium. Chemical equilibrium is only applicable for reversible reactions, and reversible reaction can exist only in the closed vessel. Now, how to identify a chemical reaction is irreversible? For example, every neutralization reaction, every precipitation reaction, every redox reaction, every combustion reaction is of irreversible reaction. For this type of reaction, chemical equilibrium does not work. Now, first understand about law of mass action. Let us suppose a reactant A and reactant B reacts to form a product C and product D. The stoichiometric coefficient of ABCD are ABCD respectively. Now, the rate of reaction is proportional to the product of active masses in the reaction, in which each term is raised to the power of equal to its stoichiometric coefficient, represented by the balanced chemical reaction is this one. Equilibrium constant equals product of active masses of product divided by product of active masses of reactants. Now, what is key? Key is the equilibrium constant. For example, we can calculate it for pressure equilibrium constant and concentration equilibrium constant. Law of mass action is only applicable for chemical reaction. Equilibrium constant is only dependent in temperature. Now the relation between Kp and Kc is Kp equals Kc multiplied by RT raised to the power del n. What is del n? Del n is number of gaseous mole of a product subtracted by reactant. For example, C plus D, that is sum of number of gaseous mole of product, minus A plus B, that is sum of gaseous moles of reactant, that is del n equals C plus D minus bracket A plus B. If Kc is greater than 10 raised to the power 3, the product will be dominant and the equilibrium shifts toward forward reaction. If Kc is less than 10 raised to the power minus 3, the reactant will be dominant and it will be of backward reaction. If Kc lies in mid value, then both will be on equilibrium. Now, if a certain reaction is multiplied by n, that is initially it has a equilibrium constant as A. Now, after multiplying the reaction by n, now final equilibrium constant will be initial equilibrium constant raised to the power n, that coefficient from which it is multiplied. Now, if the chemical reaction is reversed, final equilibrium constant will be reciprocal of initial equilibrium constant. If two reactions are added, then their equilibrium constant at final will be individual product. Now, if they are divided, simply final equilibrium constant will be Ka divided by Kb. Now let's move on to most important topic, that is Le Chatelier's principle. Le Chatelier's principle is one of the most important concepts from this chapter. What does Le Chatelier's principle state? Simply, if we provide certain states on the system, the chemical system tries to minimize the applied stress. It is not applicable for solid system or solid reaction, and it is only applicable for the system that are in equilibrium state. Let us understand about effect of concentration on equilibrium. Let us consider for this reaction, if we increase the concentration for A and B, that is, if reactant concentration is increased, equilibrium shift to reduce the reactant concentration, thus why the forward reaction is more favorable. Similarly, if we increase the concentration of C and D, if the product concentration is increased, equilibrium will shift to reduce the product concentration, that way backward reaction is favorable. If we decrease the concentration of reactant, equilibrium will shift to produce more reactant, that way backward reaction will be favorable, and similarly vice versa. Effect of pressure. As we know that PV equals nRT, that is pressure is directly proportional to number of gaseous molecule. That is change in pressure is directly proportional to change in number of gaseous molecules. For example, that del N that we calculated from this equation is equals 0. That is changing pressure will not have any kind of significant amount of change in equilibrium constant. But if we increase the pressure for any other equilibrium, that will shift where it has less number of gaseous moles and vice versa. More number of gaseous molecules on left hand side. If the pressure is increased, equilibrium will shift to reduce the pressure. The side of reaction with fewer gaseous mole will be more favorable. Now, effect of temperature. If del H equals 0, that is effect of pressure will not have any kind of significant reaction. If del H is negative, that is if the reaction is exothermic, and if the del H is positive, that means the reaction is endothermic. If the temperature is increased for exothermic reaction, it will minimize the temperature, that way it will shift towards the backward reaction. If it decrease the temperature, it will try to increase the temperature, that way it will shift toward forward reaction. Similarly, for if del H equals positive, that is endothermic reaction, if the temperature is increased, it will try to minimize the temperature, that way the equilibrium will shift forward reaction. And if the temperature is decreased, it will try to increase the temperature, that way equilibrium will shift toward backward reaction. There is no effect of catalyst on equilibrium. Constant volume, there is no effect of inert gas on the equilibrium. At constant pressure, if inert gas is added, the reaction will move in direction where the number of gaseous moles increases. Action where carbon dioxide is reacting with H2O molecule to give hydronium ion and SCO3 minus. If we escape out this carbon dioxide molecule, the concentration of H plus ion decreases, as the equilibrium will shift toward a backward reaction and produce more carbon dioxide molecules. This is the most important question from this chapter that will be asked for your entrance examination or competitive examination or theory questions. Now, the most favorable concentration for more yield of ammonia, that is from the Haber's process, is high temperature and low pressure. That is the most important thing you need to remember from this chapter. For Haber's process, Kp is less than Kc. Now here is 3 numerical that you can practice by yourself. The notes I suggest you to follow our Pinterest page or follow our Telegram channel. Now that's much for today. Bye.